Hello friends, today I'm back again to display, or I guess to talk about how to find vulnerabilities by reverse engineering actually a program. A lot of times we always have seen that fuzzing is an easier way. I like fuzzing. I believe fuzzing is a really good way of identifying memory corruption issues. It's easier to find issues with fuzzing. However, it requires a significant amount of effort in terms of setting up the fuzzer, making sure of writing the right protocol and values, and ensuring to make sure that automation is enabled correctly so that you can record fuzzing test cases, and finally you can probably exploit an issue after you identify a specific vulnerability using fuzzing. However, certain times it's easier to reverse engineer certain times programs and identify issues. It makes you a better reverse engineer, but also it helps you to identify and understand how issues can be identified even without fuzzing. And also it does make you feel a little bit better from the perspective that you're not just throwing things at a program and hoping that it crashes. You're actually trying to identify issues. So I guess different people have different motivations, and I'm not really sure what drives different people. One of the reasons that I like to look at certain vulnerabilities is that if somebody finds a vulnerability using fuzzing, that's great, but that means there's a good possibility that there would be other issues that might have been missed because the fuzzer was not able to reach to those issues, or probably you didn't think about those as inputs when you created your fuzzing file. So in this case, what I've done is I've loaded up an IDA in IDA, well, I guess IDA demo, a specific OCX file. OCX files are basically, uh, you know, um, the COM objects, the OLE COM objects that basically allow Internet Explorer to have additional functionality from program. So in this case, I'm using one of the vulnerabilities that was identified on exploit DB. In this specific OCX file, this is basically an OCX that allows you to deal with registry settings on a computer. So one of the ways of identifying the issue was using fuzzing, and it seems like the person who identified the issue um, has already fuzzed different parameters, properties, and methods, and identified one of the property that had an issue. So looking at that, I thought there might be another issue that might lurk around in the same program, and hence decided to investigate using IDA. Whenever you want to start looking at an executable or an OCX file or any other kind of program, and if you're interested in identifying memory corruption related issues, the easiest way is to look at the imports that once it's loaded in IDA, to identify the imports. What I try to like to do is basically try to find out functions that are usually known to have issues. So something as simple as string copy. And it seems like the developer of this program or this specific executable did use lstring copy A. Lstring copy A is basically string copy in Unix. It basically is string copy destination source without any bounds check. So if you do not perform specifically a bounds check, then it might result obviously into a memory corruption issue. So I guess one thing you could do is create lint string copy and then try to identify basically a graph. And so using xreps2, I was able to create a graph for this specific thing. Now obviously in a larger program you will have this as a very complex graph. Since this was a smaller OCX file, it did not have a lot of paths, but it seems like there are a lot of paths that do come to lstring copy. Usually I'm interested in seeing issues that come from functions that take user inputs in some way. And so one of the things that I did identify was dialog function. Let me try to zoom it a little bit more if you guys are not able to identify it. But dialog function is one of the programs or in the graph that seems like something that might be related to a user model window in a way. So looking at that, I thought let's investigate into dialog function and see if we can identify something that might be useful for us. And so from dialog function, it seems like there are a couple of different ways that L-string copy gets called. One way is obviously calling directly, and then the other ways are through these different variables. Now again, this is a stripped binary, so it's really hard to figure out what these functions might be doing. So I guess the easier way is to look at them in IDA. So this is the function from the dialog function that we saw in the graph, and one of the things that I usually like to do is try to quickly grab any strings that might catch my attention. So it looks like this one does show a window with text with an unregistered button. So I think looking at the program and running the program, I'm aware that this requires a registry key in a way, which is stored by the program in reg.lic file. So seems like this is related to that, and then it seems like there are different paths going through it. One thing that I observed was the fact that it called reg.lic and then jumped into an inner module. That is something that caught my attention. It seems like this would be a function that reads the value from reg.lic and possibly identifies if you have actually registered the function correctly. What I'm interested is basically in the fact to see how this reg.lic file is being read and how it relates to our L-string copy function. So looks like if you have looked at a couple of my reverse engineering examples before, what I like to do is basically identify, usually IDA is pretty good at this, so if you hover over this, IDA should be able to tell you what kind of function call is this is. So if you scroll up, it seems like IDA declares it as C declared, and the reason it does that is because at the end you can see that there is add ESP16 that defines that the caller is responsible for clearing up the stack, and it's adding 16. That means it's adding it. This specific function should be taking 4 parameters. As you can see, there's 5 pushes. There's push ESI, push ESX, and then this and this. So sometimes it gets confusing. Usually I try to identify by looking at the push instructions before the call, as that it defines parameters, but it's obviously better to understand from this. And obviously IDA is very helpful in doing that as well. That's just an example. So it seems like they're pushing LP string 1. I'm not really sure what goes in LP string 1, and we'll find out that sooner. The second thing that is pushed is the reg.lic file, the file that has a license, and then there is a one integer and the actual module, which is the program module. So this is basically a handle for the module. Once it goes in here, there are a couple of things that happen, and I guess if we go through the program, you can understand it very quickly. But this is obviously the prologue. One thing that does happen, it seems like it calls get module file name. And if you Google this, it will help you to understand that this specifically returns the path of the module. So in case when there is nothing provided in the module, then or the file name is one of the parameters. If the file name parameter is null, then it will return basically the path of the executable. So basically in this case, it seems like what this thing is doing is, if you look at these instructions, is that it's taking a size of 260 characters. The LP file name is a file name that we have to write, which is the reg.lic file. And then the H module is basically the handle module that we built. And this is where the LP file name is basically a buffer where the actual file name will be retrieved and stored by the specific function. And you can look at the declaration of the specific function in Google, and that should help you to understand that. Once you get that, it seems like, so what it's doing is basically getting the path of your reg.lic file, or basically the module which is running. In this case, that would be the reg.ocx file. Once it gets that, it seems like it's calling L-string copy, and that sort of takes my attention. It's like, okay, it seems like it's calling L-string copy. However, if you observe that it's pushing EAX, and EAX has been so again there's another function in between, and I'll explain to you quickly what that function does. Basically, it seems like the function reads and tries to find the last backslash. And the reason I know that is because there's a 5ch that's being pushed. If you look at the hexadecimal value, it's a backslash, and this is push EAX, which is basically the same EAX value over here. Remember, that would contain the whole path, the full path of your function, of your executable. And then basically it's calling this. If you look over here, it's trying to do a comparison and trying to basically identify over here that if there's a backslash, and whenever it finds a backslash, it exits out, and then basically, rather than using a L string concatenation, for some reason the developer of this program has created a L string, and this L string copy A, basically all it does is it concatenates the file path that we got from get model file name A with the reg.lic. So it assumes that the reg.lic file is actually in your directory path of your executable. Once that is done, what it will try to do is open that file, and that's because of this create file A function. IDA Pro is really good, and I really recommend using IDA. It identifies the Windows functionalities very quickly. These are basically Windows functions that are exported out, so it's very easy. And if you look at the desired access, it includes reads. That means it does indicate that it's not actually creating the file, but reading the file. If you look at create file A, it has two different modes. One is where it creates, or one is where it opens. With respect to the desired access is what it indicates. And if you look at the hexadecimal value, this is for reading, and hence I know that it's trying to read the file. Okay. So we got up to there. Once it gets to that point, what it does is basically compares the output of create file A. Usually create file A would give you a null output, which would indicate that it failed to open it, and if that happens, it jumps directly to here, it seems, which is move AX1 and then closes. So that means if the file was empty for whatever reason, so file did not exist, then it's going to exit out of there, which is perfectly fine. If it isn't, then what it tries to do, and this is where it starts getting interesting. So you can see that there's this whole block and chunk, and measures the L string length. One thing I always like to do is identify L string copy A. Now I know that somewhere it has to, in this chunk, it has to read the file, and that's because I'll explain very quickly once we get into this function that it does a read file. What I usually try to understand, or what I try to identify, is that in L string A, there are two parameters. One is the destination, one is the source. I'm sorry, this is basically the destination and source. So LP string 1 is your destination. What I try to identify is that destination on the stack? And the easier way to identify is to reverse sort of the path for this specific variable. So push EAX. If you look at EAX, it's being loaded with EBP minus 216, which means that this is a stack address that is being allocated. So that means the author is assuming that overall there are 216 bytes in that specific LIC file, and basically it's trying to basically move the value from stack to this specific value. Okay, so this is why it becomes interesting. Whenever there is a function that receives a value and it, from a stack address, that's where I find it very interesting, because there's a good chance that the author might have not performed the check, and as you can see, it's trying to load the string length, but it's comparing it against 19, and if it fails, then it goes back over here, and I'll explain to you what it's trying to do in that specification. Let's go to this specific function which does the read. And as I said, this is basically reading a file. In the beginning, it seems like it's only reading one file, 1 byte. But what the author is trying to do is basically perform a check to see if if the file is not empty, or if the string is not basically done. So if it's comparing and it's testing that if the EAX is 0, then it's jumping down straight away. Otherwise, it comes over here where it has read 1 byte, puts it in EBP plus 12. Now, this is where the author is doing an interesting thing again. It's seeing if after 1 byte is there a /n/r, and that's because it's doing a comparison against 0AH and 0DH. And if it is, then it exits out by reading the next few bytes and exits out. However, if it isn't, then it tries to keep on reading this specific file, until it basically finds a 0A0H, and that means it's a /n/r, and it exits out by reading the last byte. And so this is for sort of unknown bytes, or an extra byte that might exist after the /n/r. So basically the author is, so if we understand the format of the lic file or the .lic file, it seems like the registry value, or the registry key, is going to be just a single line, and after that the author doesn't expect anything to be present, so after that it only reads 1 byte and then basically exits out. However, if it doesn't, then it basically tries to do an AND over here with the value and EDI. And EDI is basically the overlap bytes. It's basically, if you look at read file, it defines the number of bytes that are overlapped in this case. So it tries to do an AND with the overlap bytes and then basically jump again and exit out. So in this case, what it's doing is it's reading the file until it finds a /n/r, and excuse me, it's doing a test EAX, which again, as usual, defines if the read file is successful or not. If the read file is successful, then it will indicate the number of bytes, which is non-zero. If it is 0, that means it did not find a 0AH, 0DH, but did find a null byte, and so the string has terminated, and as a result of that, it basically goes and jumps over here and does a AND to add that null byte. That's what it's basically trying to do. And so if you look at this specific function, once it does a read file, as we had seen, it comes out, it basically tries to do a string length. So we can see obviously that EBP-816 is the same address that was pushed into read file, and read file's address is used to do a string length. What it's trying to do is it's ensuring, and this is interesting, like you would assume that he's doing a comparison. So it's making sure that the number of bytes that have been read are not greater, or actually it's basically the number of bytes that have been read have to be greater than 19. If it's greater than 19, then it will jump to your lstring copy. However, if it isn't, so I'm assuming the author might have written some kind of a check function which says if lstring length, pardon me, I guess I'm typing it out, but this is lstring length. If the number of bytes read, which is this, is greater than 19, then do the string copy. Otherwise, ignore it, and that's what the author is doing. So he's actually not assuming that the rec.lic file might, if it contains less than 19 bytes, obviously, then it's exiting out. That means it's assuming that it's incorrect byte. However, when he's doing an lstring copy A, he's not performing a proper check on the number of bytes. And so, if the number of bytes are, obviously greater than 216, that means you're going to overwrite over, the EBP, and then obviously the saved values, which is the return pointer, and basically at that point of time, you should be able to execute shell code. So, however, with respect to this, there are a couple of things that happen. Once this lstring copy A happens, then there are the comparisons that need to go through. He's checking again for making sure that there is no space, and then finally there's another lstring copy A which also does the same thing. It's copying the value, and this is again a stack value. And finally, so based on our understanding, Again, this is not an exact science. This has to be, reverse engineered. As you start doing reverse engineering a lot more, you start realizing the patterns. But usually, the pattern that you want to make sure is that if there is something that can be read from one of the input values that can be provided, in this case, this is a file, and if that value is directly being put on a stack, and there's no comparison, there's a good chance you can control the EIP at that point of time and execute. So I guess a good way is to quickly demonstrate that. And so I've already done, in this case, in the beginning, when you try to load something, you don't want to have, the reg.lic file present, and that way you can load the specific thing. So in this case, I'm going to load the ActiveX. So in this case, for loading the ActiveX, it's very simple, and I'll show you how to load an ActiveX file using JavaScript. So it's a very simple file. All I'm doing is I'm providing class ID and just calling one of the properties, and that loads that specific file. The reason I want to do that is so that I can do a break, find executable module. So what I'm going to do is find name, find the reg module, which should be loaded now, and then put a breakpoint on one of the addresses when it's doing the lic. So remember that we were looking at the L string copy A, which was this function, and remember there are two L string copies. So I'm going to put it on the second L string copy because even after the first L string copy, it has to go through all this, and finally when it does a close handle, it basically tries to do a final L string copy A, and then basically does a close handle and tries to exit out. It basically tries to compare and test, and when it fails at this test, if you look at it, there is a JZ, if it fails, it basically jumps over here. And that's what we are interested in, because obviously even after writing over the stack, there has to be a way out of the function so that it can do a return, and when it tries to do a return, that's where we know that it gets screwed over. So let's do that. Let's put a breakpoint on this specific code. What I'm going to do is going to highlight this and then do a text view and find out. So it looks like it's 89C5, and remember this is not the actual address. The actual address is the RBA, which is 89C5, and so we'll have to substitute that correctly over here by doing so we are in wedge module, we want a 2010F 89C5, and it's calling call ESI, which resembles the same thing, but in this case it is L string copy A, which IDA has identified. What we are going to do is now we are so this is a string copy file, that reg.lic file that's already created by me, and I'll also show you the exploit that I wrote for this very quickly. All I did was, and this is where I've identified obviously by doing shellcode exploit, where the actual EIP controller needs to be there, and then basically I'm inserting a calc payload, so this just pops up a calculator, because I only have 380 bytes that I can use. I mean, there are more bytes obviously, but this is what I have that I can do handily and quickly my stuff. The reg.lic file has been, and we can open the file as well just to understand very quickly. That's basically the same thing. As I said, there is pointer and this is the file. What I'm going to do now is copy the reg.lic which is created into this specific folder and then reload. And when we do a reload, it seems like it has paused. And you can see that this has a part of the string. What I want to show is a part of the string has already been copied, and that's because of the fact that we had so if you look at this was the first L string copy A that has copied my stuff and overwritten pretty much the values, and this is the shell code. This is my shell code of calculator that is already present now. And now This is also again another few C's that have been copied in the stack. So what we're going to do is we're going to let this copy run and then do an else string copy. And so now if you look, the stack would be overwritten again with our values, and pretty much the stack has been overwritten with our values all over. And so if we do this, remember the kernel calls close handle. We'll go through different things. One of the things that we were looking for at that time, and we go back to our function graph view, close handle is being called. We are trying to see if we can exit out over here. And so we'll see. Now obviously this is my understanding that it should exit over here, but if it doesn't, it will exit out at this point from here, because it does a comparison, and this is the function that does the registry check and make sure that the key that has been provided is the correct key, and that doesn't match up, and so it exits out. So either over here or either over there it should exit out, because we don't definitely have the right values. And so let's do that. Let's see where does it allow us to, basically exit. What I'm also going to do in addition to that is, if you look at my breakpoint file, exploit file, I have a breakpoint over here. This is the EIP value, and so I'm going to also put a breakpoint over there just in case if we miss out. Okay, so let the stack continue executing. It does this. It says jump is taken, so it goes up. Like I told you, it misses. Obviously, we don't. If you remember, this is the JE. I'm going to find that over here. Test EX0C, and so this is where it moved, and it moved to this specific. Now currently it's pointing over here, move AX1. There's a JE that resulted in that jump to this specific point, and we want to make sure it's the same jump that we were thinking. And remember, compiler and IDAPRO and OLEdebug will take the same thing. IDAPRO calls it as jump is equal to 0, while our OLEdebug, in this case Immunity Debugger, calls it as jump is equal to. And so it seems like when it read the file, it did a else string copy, it did close the handle of the module, assuming that it's completed. It did compare against this. And so this is one more function that does a comparison, like I said, for the values inside the key. In a valid scenario, the key would have been the right key, and then it would have gone further. But since it did not find the right key, it exited out of that, basically did an add 0ch. This is basically, again, keep in mind this is this takes 3 parameters. That means this is clearing of the stack, and it does a test EX. When it finds that it isn't, it moves over there, which is move AX1, and it's going to return. And this is where the things get interesting for us, because now when it goes over there, we can see that it's doing the regular thing, turn, and you can see that ESP is pointing to my 614864B4, which is what I have used as jump ESP pointer. And there you are. And now if we do this, and we are in my NOPS, and booyah, calculator popped up. So this was basically a quick exercise of how we can use both dynamic analysis, which is running the program in Immunity Debugger, but then reading the program a little bit in the beginning to identify functions that are vulnerable, and then using those functions to identify if there's a path to get to those functions from any of the input values that user can provide. And so in this case, it seems like if I provide a reg.lic file, which is corrupt reg.lic file, then I can control basically the IP and basically exploit the specific OCX file. Again, this is basically a small tutorial and example basically to show how reverse engineering can help you to identify vulnerabilities. If you like this one, that would be great. That it seems like I'm doing my job. I'm trying to help people out by myself, obviously learning it, but at the same time trying to help other people out as well who are interested in learning this. So thanks again for watching the video. Have a good one.